Alright, so the next one is the 12th one. In this one we have to find all possible Jordan forms for all 8 by 8 matrices which have this polynomial as minimal polynomial, that is part A. And in part B for all 10 by 10 matrices which have this one as their minimal polynomial. And here the underlying field also has characteristic different from 2, which ensures that -1 and 1 are different, they are not equal to each other. We are only going to solve part A, part B is similar, it will be left to you. I will give you one hint though. So let us now start part A. Start part A means let's first see what this polynomial gives us. So the distinct roots of this polynomial of course are 0 and 1. Now if it has to be the minimal polynomial of a matrix or a linear operator, an 8 by 8 matrix, then that matrix must have 0 and 1 as its characteristic roots. So in the Jordan form of that matrix or that operator, any basic Jordan block has to belong to either 0 or 1. That's the first thing. The second thing is that 0 has multiplicity 2 as a root of this polynomial. So any basic Jordan block belonging to 0 can be of size at most 2 by 2. It can be of size 1 by 1 or 2 by 2, but not more than that. Similarly, any basic Jordan block belonging to 1 can have at most size 3 by 3, not more than that. That's the second thing. And the third thing is that because this has to be the minimal polynomial, so there must be at least one basic Jordan block belonging to 0 of size 2 by 2, and that is the maximum possible size, and at least one basic Jordan block belonging to 1 of size 3 by 3. Keeping these constraints in mind, there are quite a few matrices, 8 by 8 matrices, which are in Jordan form. One of them is this. So here you can see that there are 3 basic Jordan blocks belonging to 0, which are this, this and this, and one basic Jordan block belonging to 1, which is this last one. The first 2 blocks belonging to 0 are 2 by 2, this one is 1 by 1, and the one belonging to 1 is 3 by 3. So yes, there is a block belonging to 0 of maximum possible size and one of belonging to 1 of maximum possible size. So all we have to now do is we have to list all these matrices. How many possible ones are there? We have to write them down. But if we use this normal notation, it will take a lot of space. So let us first fix the notation. We are going to need a smaller notation. So accordingly, let's start the solution by writing about notations first. First of all, we are going to give some name to basic Jordan blocks. Already we are calling them JI or something like that, but we need a better notation. Let Jn of lambda be the n by n basic Jordan block belonging to lambda. And you already know what that thing is. It is that n by n matrix whose diagonal has only the lambdas, super diagonal has only ones, and elsewhere it's 0, which is what you see. For example, you can see here. This one belongs to 1, that is we have 1 in place of lambda. So 1 along the leading diagonal and 1s along the super diagonal super diagonal, and elsewhere it's 0. So by this notation, this is J20. This one is also J20. This one is J10. And this last one is J31. Now we can write this block diagonal matrix as J20, J20, J10, J31, but still it takes space. So to further compress it, let us also use this other notation. Also, let Bn denote the block diagonal matrix this. So with these new notations, how does this Jordan form look? It now looks like this: J20, J20, J10, and J31. Okay, so that's how we are now next going to write all the possible Jordan forms for 8 by 8 matrices, which have this one as their minimal polynomial. One of them, of course, is this. We are again going to write it. In finding these matrices out, I have not really followed any scheme, or you can understand what I'm trying to say. I just have kept in mind that we have to have those two basic Jordan blocks, that is J20 and J31 should be there, and besides those two, you can then change the others, and there only you have to see how many possibilities are there. So these are the matrices. Without writing anything more, let me just write the matrices down. J20, J10, J31. And then we have J20, J20, J31, J11. All right, next J20, J10, another J10, then J31, J11. To make this list look better, I am not going to write from here. Okay, so I am writing like this so that you can distinguish between these things better. Okay, so how many have we written? 3 only, but there are others as well. J20, J10, J10, another J10, and then J31. you can see that we are keeping all the constraints intact. In particular, there is at least one J20. So far we have written 4. In each one of them there is at least one J20 and at least one J31. It should be like that. And then J20, J10. Let me see, I should not write something wrong, okay. 1, 2, 3, 4. 2, 3, 4, okay. Then J31, J11, and another J11. One more thing you can check to see if you have written something correctly is that if you add these indices, add these suffix values, you should get 8. 2 plus 2, 4, 3 plus 1, 4, 8, like that. For example, this one, 2 plus 1, 3, 3 plus 3, 6, 7, 8. Then J20, J10, J31, J2, 1. Next, J20, J31, J31. You can see that in this last one means it's not actually the last one. There are others also. 2 more are there. But here for the first time, J31 has appeared twice. In the others we have seen, for example, in the very first one, J20, 2 copies of that are there. But here 2 copies of J31 are there. And so 3 plus 3 is already 6. But that remaining room is filled by this J20, which also has to be there, at least one. Then there are 2 more. J20, J31, J21, J11. This one is also somewhat interesting because here you can see that all the possible sizes of basic Jordan clocks belonging to the characteristic root 1 are available. 1, 2, 3. And finally, J20, J31, J11, J11, and another J11. Now, I want you to do something about this itself. Of course, for space constraint, we had to write things like this. But I want you to really write all these matrices in their actual form, in their old notation, the actual notation, and see how they look. You see for yourself that in each Jordan form, J20 is there and J31 is also there, but the other things are changing. How they are changing, I want you to see that and figure out a scheme for systematically writing this list. I have already said now that I wrote this thing somewhat haphazardly. So you try to find a systematic scheme and do this. Rearrange the list. Part B is similar. It is left to give. The hint I am going to give about this is that there are 20 Jordan firms here. The number is much more than this. Here there are only 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. But here there are 20 because more possibilities are there. Also, there are 3 distinct characteristic roots 0, 1 and -1. That is why. Now let us see the next one. Let's see another one. 13. Prove that the n by n matrix A all of whose entries are 1. In the book, the matrix is drawn or written in its form. I am, however, writing in words because it's easier. R1 is similar to the n by n matrix B whose first row first column entry is n and all the other entries are 0, but there is one condition also. If f is the underlying field of scalars from which the entries are coming, is of characteristic 0 or is of characteristic P, where you know what P is a prime, and P does not divide N. This last condition or the characteristic of the underlying field is there to simply ensure that this first entry, first row, first column entry of B is not equal to 0. If the characteristic is 0, of course N is not equal to 0. But even when the characteristic is P, P does not divide N. So in the underlying field, N is not equal to 0. That's what this condition ultimately tells us. Moreover, what is, and in fact, the non-zeroness of N is required for this next part. What is the multiplicity of 0 as a characteristic root of A. All right. So here the solution is not that big. We will just have to write the matrix that will give us this similarity. That's it. If you want to see how the matrices look for a small value of n, this is how they look. Say n is 3, then this is A, and this is B. That's how they look. Now let's see the solution. Consider the n by n matrix, let me call it C, whose first row is having all ones, and then the second row is 1 minus 1. It has 1 and minus 1, and the other entries are all 0. And then this 1 and minus 1 shifts 0, 1, minus 1. The others are 0. And like that it goes. Finally, in the last row, it's just 1 and minus 1. Before this minus 1, there is a 1 also, which I am just showing here. Okay. Say this is our n by n matrix C. Now it's just a matter of verifying that this C is the matrix that gives us the similarity between A and B. One can verify that CAC inverse is equal to B. You can verify this equation more easily by instead showing that CA is equal to BC. But that alone won't give you this. You also have to somehow make sure that C is invertible, about which I am not going to say anything. Okay, I leave that also to you to figure out why C is invertible. But this is the fact. Hence, A is similar to B. Now, because A and B are similar, they have precisely the same characteristic roots. Now, if you look at the matrix B, I mean it's n by n version, here it's 3 by 3. There you will have n here and all the other entries are 0. Now, since this is a diagonal matrix, you can clearly see what its characteristic roots are. For this specific matrix, they are 0 and 3. I say and 3 because 3 is non-zero, and that's why we need those conditions. In general, n is non-zero. So, as a characteristic root of B and hence of A, because they are similar, the multiplicity of 0 is n minus 1. In this case, it is 3 minus 1, 2. And that's why we write so. As a consequence of this, the multiplicity of 0 as a characteristic root of A is n minus 1. That's it. There are still more exercises that we will solve next Saturday. And tomorrow, as usual, we again have analysis. And tomorrow we are going to start that section where we will see the two fundamental theorems of calculus. So this is the part which will remind you of things from your school days, school calculus courses. So that's just it for tonight. See you tomorrow with that fundamental theorems of calculus. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.